Welcome back to California State University, Northridge, the Department of Chemistry and Biochemistry, the Chemistry 101 Laboratory Pre-Lab videos. I'm your host, Alex Jason Machinota, and this will be the last of your experiments. So you're almost done, and we'll go ahead and dive right in. So most of today's experiment can actually be done on paper. I'm just going to go ahead and go over some of the things that you're going to need to understand to do that and to actually completely do experiment number 10 correctly. So if you'll go ahead and open up your Chem lab manuals, flip to experiment number 10, and join me on figure 10.1, which will look pretty much like a periodic table, except you're going to notice that all of our elements have numbers directly underneath them. Now, what those numbers are the Pauling electronegativity. So it's kind of an arbitrary scale based off of data that we've collected over the years that tells us how electronegative atoms are. And electronegativity is that atom and that element's propensity to go ahead and pull in electrons. So how much it actually wants to go in and grab an electron like it is a delicious sandwich. So if you look at it, there's some trends. Now, as we go up and to the right, so as we go up our periodic table and to the right, our electronegativities increase. So the least electronegative atom is going to be francium, which is all the way on the bottom left. That's Fr on the bottom left, atomic number 87. Now, the one that's going to be really, really hungry for those electrons, it's just going to be wanting to snatch anything in its sight, is going to be fluorine. And fluorine is on the top right. Now, I'm saying that these are trends. They're not exact numbers because some of them don't really follow the exact trend, and they're for different reasons, such as like the noble gases. The noble gases usually are not going to have any electronegativity because they usually don't bond, but some of them you can get them to bond if you have a strong enough electronegative atom, and we're going to actually see that in this lab. So that's electronegativity. The other thing that you're going to have to know is the intermolecular forces. And the intermolecular forces, most of them actually derive themselves from electronegativity. Now, there's three forces that we're going to go ahead and talk about today. And these are the three main forces that we will see. The first one, if we go ahead and flip a few pages over to table 10.2, is your permanent dipole. So that is pretty much your polarity. So if you have two atoms that have a significant amount of polarity difference, actually any polarity difference, any electronegativity difference, you're actually going to see some polarity in that bond. Now, when we're talking about polarity, we also have to think into account the entire 3D structure. So things that are completely symmetrical, say CF4, that, even though carbon and fluorine have a pretty big electronegativity difference, is going to be nonpolar just for the sake of having every single atom around that carbon being exactly the same. So when we're talking polarity, you have to think two things: difference in electronegativity and 3D shape. Now, the second intermolecular force is hydrogen bonding. So hydrogen bonding is this additional attraction that comes up between very, very polar bonds that include hydrogen. And there's a few atoms that do this. Oxygen is one of the most important ones. Fluorine does it, as well as nitrogen does it, and then chlorine to a very, very small extent, sulfur to a small extent, but for the most cases, we're going to only talk about oxygen, nitrogen, and fluorine. Now, hydrogen bonding, again, you need to have a direct bond between hydrogen and either oxygen, nitrogen, and fluorine. And what will happen is that since they are big differences in electron negativities between hydrogen and any of those atoms. Hydrogen is going to have less electron density on it, meaning it's going to get a partial positive charge. That'll make the other atom, we'll say oxygen in this case, be partially negative. So when another water molecule or another molecule that has a hydrogen bond approaches it, those positive and negative ends are going to kind of stick onto each other and increase the attractions between the two molecules. So that's what we see in water, and why water has such a high boiling point. The last intermolecular attraction that we're going to talk about is London dispersion forces. Now, every single atom and every single element has London dispersion forces, and it doesn't matter what size the molecule is. And London dispersion forces pretty much come up from the fact that we have electrons buzzing around nuclei. And the fact that we have some positive charges and negative charges means that when things kind of get close to each other, you're going to have some interactions between them, even if they're not in the same molecule. So forces can kind of stick to each other depending on what their London dispersion forces are. But for the sake of today's experiment, we won't go into it any deeper than that. Now, the last thing we're going to talk about is our VSEPR geometries and how to use the table that we see that's listed under table 10.1. So this will probably be before table 10.2, but we went a little out of order. It's okay. Now, on this table, we can pretty much figure out the geometry and therefore what type of intermolecular forces we are going to have based on the electron pairs on the central atom. So we'll read this, and you'll notice that first there are 4 columns. At the very top it says the number of electron pairs, the electronic geometry, the molecular geometry, and the approximate bond angles. So you'll look at your central atom, and your instructor will talk to you about how to figure out the central atom. There's also a list of instructions that are given in your lab manual. You'll notice how many electron pairs are around your central atom. So how many bonds or double bonds are around, and lone pairs are around your central atom. So you'll say, okay, if I have 3 pairs of atoms, electron pairs, around my central atom, my electronic geometry, electron pair geometry, is going to be trigonal planar. Now, if one of those is a lone pair, then your molecular geometry is going to be angular or bent, depending on what you want to call it. If you have no lone pairs around that central atom, just going across your table here, you're going to have trigonal planar. Now, if it's trigonal planar, your angle is always going to be 120 degrees. But if it's bent, it's going to be less than 120 degrees. So that's how you read that table. You just go straight across, basing it on how many electron pairs you have around that central atom. That is probably all we're going to go over in this video. And we'd like to thank you for the semester. If you have any other questions, please feel free to email your instructor. Talk to them before or after class. Talk to them during office hours. And, you know, have fun with this experiment. You're almost done. And we will see you for next lab.